Greetings, dear colleagues. Today I want to present you the results of our study on Bremsstrahlung emission in proton-deuteron scattering and nucleon forces that we have done using some cluster models. We have developed the model based on the cluster models in nuclear physics for analyzing and for getting and analyzing the spectrum and cross-section of the Bremsstrahlung emission that can be produced in proton-deuteron scattering. As well as we can use our model to analyze the structure of the nucleus in deuterons. And also we can analyze the existing experimental data and provide some new points, well, specifically the energy of beams, to get more data for our model. As you can see, our model is a continuation of the based on the cluster. So first of all, I'll talk a bit about the theory behind our approach. So as first we have the Bremsstrahlung emission. It's in the process of protons scattering on deuteron, the collision. We have a chance of emitting a photon with some polarization and momentum, the transfer momentum of the collision, and this is the photon creation operator of such process. We are sitting here in the center of momentum frame, when the most important part are the operators that are mainly here for creating a photon. In order to calculate the cross-section of the emission, we need some wave functions for the deuteron and the relative motions of proton and deuteron in our process. So we use based quantum mechanics, Schrödinger equation, both for the deuteron, for acquiring the wave function of the deuteron, and for acquiring the wave function of relative motion of proton and deuteron in our process. And the next, we calculate this nomenclature for our using different models. Here there are some used cluster models, 2 and 3 cluster models, and also folding potential. And then we use these wave functions, and on the right side of the screen you can see the detailed form of the operator of the photon creation in the process, and we calculated the matrix elements to get the cross-section of the photon emission during the process. For the models, we used a folding model to get the wave functions of the deuteron and the wave functions of the relative motion, 2 cluster and 3 cluster model as well. Also, for the folding model, we used the model as very straightforward approach with simple Schrödinger equation for both the deuteron wave function and for relative motion. Also, we use as for the nuclear forces, we use the Minnesota potential in our calculations. As for this 2 and 3 cluster models, the approach is pretty much the same, but our wave functions should satisfy the following. The following condition to be correct, and also for the 2 cluster model, we used a simple approach with that more or less like a shell model, where we use an oscillator length as our parameter that can which can give us more information about structure of the deuteron right here. This is a wave function of the deuteron. And so we can now calculate and analyze, for example, we can calculate and analyze the wave functions, and we start with deuteron wave functions. Here we have results of our calculation for shell model. It's also known as, we call this the shell model. It's more like a two-cluster model and three-cluster model, and we can see that even if they're pretty close, the behavior of the wave function on the logarithmic scale is quite different. And we find that cluster model are more accurate for this than helpful future calculations. Also, we calculated several wave functions with different energy for relative motion. With in the states of 1 over 2 plus and 1 over minus, and this is the wave functions of relative motions in several. We need this all for the future calculations of the matrix element, which I shortly will come to. Yeah, and so you've seen the big operator, detailed operator of the photon creations. Here are the main matrix elements or form factors that we need to calculate to get the probability of photon emission and the general cross section of the Bremsstrahlung emission in the process. Two form factors are completely independent on the wave function of deuteron and wave function of relative motion, so we can calculate them separately. And we did that. For example, on the next slide, here is our comparison between two-cluster model, shell model, and three-cluster model on different scales. And we can see that the three-cluster model gives us additional node on the form factor of the emission. And this node is give us a bit about information about the structure of the deuteron itself. So our final idea was to also to comparison our results with existing experimental data. Here we have the experimental data for proton-deuteron scattering at energy of the beam 145 MeV. And we can see this, the triangles is experimental data, and the green line is our current calculation, and the dotted red line is its previous calculations used in this work by Python. And we can see that our calculation is some areas are fitting pretty well. Well, this was for the folding potential, as we have calculated that folding potential and shell model and two cluster models give us exactly almost the same cross section of the emission. Here we can only compare the two cluster and three cluster models, and also we have this previous one with experimental data, and also we have chosen two different beam energies for calculation the cross section of the emission. Also, we can vary the oscillator length, the parameter in our wave functions, and we can see that the results of the calculated reverse section is a bit different for different oscillator lengths. So it is possible for us, if we can have access to the more experimental data with higher energy of beams, we can analyze and understand which structure, which oscillator parameter, oscillator lengths are better for describing the inner structure of deuteron from the cross section, the spectrum of the Bremsstrahlung emission. for the photon emission during the breaking. Also, there was one small work with another form factor, another wave function. We just and it appears that it's completely the same as the calculated spectrum with zero. So with such a parameter that is zero, it gets this result. And also you can see it here. That's it. And as a result, we have investigated the emission of Bremsstrahlung photons in the proton-deuteron scattering. And we have calculated this for several energies, as well as for existing experimental data with 145 MeV and up till 105 GeVs. Also, our model includes the form factors of deuteron that can be used to analyze the data on the Bremsstrahlung emission, to analyze the inner structure of the deuteron and also the parameters of nucleon-nucleon potential interaction. And in our study, we use oscillator length as a parameter for analyzing this influence. Also, we get quite distinguishable differences between cross sections for different value of our parameter for 500 MeV and above. As you can see here, the strong lines distinguished quite a bit. Also, we can see the perspectives for our work. For example, we can propose several energies and for new experiments to obtain more data for more high energy beams, for example, 500 MeV or above. And also for the future, we can include the magnetic moments of nucleons for future studies of dependencies of the cross sections on of this magnetic moment. Also, we can use this study as a basis for more scattering, for heavier nucleons, not only proton and deuteron, but proton and helium, and etc. This is it from me. Thank you for your attention.
Okay, thank you. Please, we have time for questions. Let me start. I have the same question as for the first talk. In two-cluster model, as I understand, you have proton and deuteron as different objects, but still, a question is, do you take into account Pauli principle between outgoing proton and proton inside deuteron? They should satisfy Pauli principle or not?
Well, as you said, there are two different objects, and even if we have in two-cluster model.
And I understand if you have three-cluster model, this is a model for three different nucleons. Then these two protons should be anti-symmetrized in some wave functions. But if you have two-cluster model, you have proton and deuteron. Inside deuteron, proton may be some quasi-particle with effective mass and something like that. So it is essentially different from outgoing proton. And the question is, do you do this anti-symmetrization or not? This is a question.
Yeah, we have done this right here.
You do?
Yeah.
Okay, why? But if inside deuteron, proton is quasi-particle with mass 0.5 of proton mass in vacuum. So this is quite different object. And why should I take anti-symmetrization of one proton in vacuum and another proton inside nuclei? It is quite different objects.
Are you talking about two-cluster approach or three-cluster approach? I don't quite
my
understand.
question is for two cluster model,
For two cluster model,
where you have proton and deuteron as two different objects.
and if the three protons that are scattering are antisymmetrized with the proton inside the deuteron, right? Am I correct? Am I understand your question correctly?
Let's switch to Ukrainian language.
Е,
Моє питання таке: протон, який налітає на deuteron, на дейтрон, це протон in vacuum. Його маса дорівнює масі протона in vacuum. Протон, який знаходиться у дейтроні, це вже дещо інший об'єкт. In some models it має таку саму масу, як протон у вакуумі, в інших моделях це може бути інша маса. Тобто це вже не вільний протон, а це протон у середовищі. І тому незрозуміло, чи потрібно чи ні антисиметризувати цю волнову функцію. Ви відповіли, що ви її антисиметризуєте. Якщо це
I understand the question now. So in three cluster model, we antisymmetrize it 100% sure. In two cluster model, I think we
The same.
the same. Yes, we have done the same as I answered before.
the same, what do you mean the same?
We antisymmetrize the proton.
Antisymmetrize
Yes.
also.
Yes. Yes.
Why?
Also.
Question why? Які фізичні аргументи для цього? Це різні об'єкти. Один – це вільний протон, інший – це квазіпротон, чи протон всередині якогось середовища, всередині...
Зв'язаний.
Здається, що це різні об'єкти, їх неможливо переплутати, тому незрозуміло, чи потрібно, чи ні, їх антисиметризувати. Ну, добре, ви антисиметризуєте, я зрозумів.
Yes.
Інше питання таке, коли ці фотони випромінюються, то у вашому формалізмі це у кожній реакції тільки один фотон випромінюється, чи може бути багато? При цій енергії 145 МЕВ, скільки фотонів в одній реакції випромінюється? Один чи більше?
One photon per one reaction, but there's a probabilistic process, so maybe it can be produced or cannot.
Моє питання таке, це, наскільки я зрозумію, це експериментально відомо, скільки у середньому фотонів випромінюється у такій реакції. Моє питання таке, це один в експерименті, чи 1,5, чи 2? Це спектр. Але спектр ви отримуєте, сумуючи мільйон реакцій. В одній реакції, в одному зіткненні протона з вашим дейтроном при енергії 145 МЕВ. Скільки фотонів випромінюється? Строго один, чи близько до одного, чи 10? Скільки ваш формалізм враховує тільки одне?
Реакцію випромінювання одного фотона за
одного
одну
фотона.
реакцію.
А скільки експериментально? Це має бути відомо, що в експерименті це теж один. Або 10. Якщо 10, то як це може бути, що ви спектр описуєте? Сорі?
Якщо 10, то ми не повинні, тоді наша теорія не попаде в результат.
Ні, це невідомо. Можливо, що ви випромінюєте по одному, а якщо просумуєте мільйон зіткнень, то отримуєте цей спектр. А можливо, що випромінюється по 3 фотони в середньому у кожній реакції. Але в деяких 1, в деяких 5. Ну, тобто ви не
у середньому у нас 1 фотон на реакцію.
У вашому формалізмі. А скільки в експерименті? Це відомо чи ні?
Напевно, так.
Напевно, так.
Але
Добре.
я не можу зараз відповісти на це
Хто ще
питання.
хоче задати питання? Будь ласка. Можна англійською, можна українською. Так, ніхто не хоче. Добре, тоді я дуже дякую вам.